What if I told you that almost everything you see in the night sky, the stars, planets, and galaxies, makes up less than 5% of the universe? The rest, the other 95%, stays invisible, untouchable, and unknown, yet it dictates everything we observe, from galaxy formation to the ultimate fate of the cosmos. Why does the universe we can't see matter more than the one we can? And how are scientists trying to uncover forces they can't capture with light? That's the journey we begin right now. Everything you see in the night sky is only a thin skin of reality. So what's underneath it? The stars that glitter, the haze of the Milky Way, the glowing planets, all of these form the visible structure of the cosmos. But this is just the surface. Beneath it lies a hidden framework that we cannot see, yet it shapes everything that unfolds above us. The question is not only how much of the universe we perceive, but whether the light in the sky has ever told us the whole truth. Ordinary matter, the kind you and I are made from, is what we call baryonic matter. This includes the atoms that make stars burn and planets solid. It forms cosmic dust clouds, gas streams, and the sparks of galaxies that shine across the electromagnetic spectrum. Telescopes detect this glow, visible light for starlight, radio waves that reveal hydrogen gas, infrared to peer through soot and dust, X-rays from the violent outbursts of dead stars. Each instrument captures a different layer of the visible universe, but all of it still belongs to the same familiar category, ordinary matter. But as telescopes improved and pushed deeper into space, astronomers uncovered a profound mismatch. What they saw did not agree with what gravity predicted. Measured mass in galaxies and galaxy clusters seemed far too small to explain the immense gravitational pull holding those structures together. Space shouldn't look the way it appears if only the matter we see is doing the work. Something vital is missing from the picture. It's like standing in front of a theater stage. The painted backdrop is stunning, convincing, and rich with detail. To the audience, it looks like an entire world. But walk behind it, and you'll find empty space, wooden beams, and scaffolding that isn't shown at the front. The visual scene only makes sense through hidden support. The cosmos turns out to be the same. The luminous stars and galaxies are the stage scenery, shallow, without the invisible structure behind them. Take the stars at the edge of galaxies. Based on Newton's laws of motion and gravity, you would expect them to move more slowly than stars closer to the center. But what we see is the opposite. They race around at speeds far too high to be bound by visible matter alone. If only ordinary matter held them, these stars would escape and galaxies would unravel. Instead, they hold together, orbit after orbit, as if something unseen provides the extra glue. And if we look into our own galaxy, the Milky Way, the deficiencies of vision become even stronger. An optical telescope operating in visible light can barely cut through the thick curtain of interstellar dust that fills the galactic plane. The farther one looks toward the center, the more light is blocked. It's as though an enormous fog covers the middle, hiding both stars and structures that make up the bulk of our home galaxy. Infrared telescopes can see somewhat farther, but even then, limits remain. Distance compounds the problem. Light from the far edge of the Milky Way grows faint, distorted by clouds along the way. What we can map remains patchy, incomplete, and uncertain. This means that no matter how advanced our lenses become, we are restricted by light itself. Dust blocks it. Distance dims it. Some regions of space simply do not emit light strongly enough for us to ever see them. For a time, astronomers assumed they simply needed better instruments or bigger mirrors. But as evidence mounted, it grew clear that visibility was not the full issue. The matter available for light to reveal was not enough to explain cosmic behavior. Indirect lines of evidence piled up. Stars and galaxies moved as if enormous amounts of unseen mass surrounded them. When clusters of galaxies drifted against the more distant background, Their gravity bent and distorted the incoming light, a phenomenon now called gravitational lensing. The distortions pointed not just to the mass that could be counted through stars, but to vast amounts of invisible matter exerting pull from the shadows. Light might never show us what lay there, but gravity would not let it hide entirely. These observations forced science to a hard conclusion. Visible matter alone cannot give the full story. The universe, as luminous as it appears, is not built from what we see. The bright face of the cosmos is only a fraction of the whole, and the vast majority, order after order more, remains concealed from any telescope that depends on light. This raises a deeper tension. How can something invisible control outcomes so decisively? Galaxies form, cluster, and curve space into lenses at scales utterly beyond what small quantities of atomic matter can explain. Yet human senses and instruments are tuned almost exclusively to light. Straightforward observation is powerless here. Instead, we have to read the universe like an engineer reading stress patterns on a bridge, by how beams bend, by how forces shift, not by simple sight alone. Imagine standing at sea level and gazing at waves rolling to the shore. If you judged the depth of the whole ocean only by its surface ripples, you would assume it was only a few meters deep. But drop a sensor below, and you discover vast unseen water pressing in from every direction. The cosmos is just as misleading. The glitter of galaxies is real, but it represents a thin, decorative skin compared to the unseen mass and energy that fill the depths beneath. Today we know that visible matter is less than 5% of the universe. That means every star, every flame of gas, every galaxy we can chart across the entire expanse is only a token layer, a trace on the edge of the true whole. 95% remains dark, unknowable by light itself, yet ruling everything from cosmic birth to cosmic fate. And while the stage we see is dazzling, it's the hidden scaffold that sets the play in motion. This is the turning point. Once we recognize that light shows us less than 5% of what exists, the next question becomes unavoidable. What fills the rest? If galaxies behave as though vast reservoirs of matter are anchoring them, yet that matter gives no light, we are pushed toward one of science's deepest enigmas. That mystery has a name. It is dark matter. And to trace its first signals, we return to the earliest hints of missing mass. Imagine standing back and watching an entire galaxy spin. Billions of stars circling a common center, light arcing like a spiral pinwheel across deep space. By the laws of gravity and motion, it should not hold together. Those outer stars rush far too quickly to remain bound. You would expect great chunks to pull free and drift away, yet they don't. The disks remain whole. The galaxies survive. Something hidden must be holding them, as if an invisible hand grips the rim and keeps it all from flying apart. This puzzle did not begin with single stars. It started with clusters, vast families of galaxies bound in groups. Astronomers measuring the speeds of galaxies inside these clusters found that visible matter was not enough to hold them in their orbits. If you added up the mass of all the stars, gas, and dust you could see, the total fell far short of what should be there. By ordinary reckoning, the gravitational pull tying the group together was too weak. The cluster ought to scatter apart into open space. Instead, it stayed stable. The evidence pointed to hidden mass on scales larger than a single galaxy. The math was explicit. Calculations of speed and gravity gave one answer, sight gave another. The numbers refused to align with what eyes alone captured through mirrors and lenses. This inconsistency became impossible to ignore. If clusters of galaxies were surviving together while shouldering that much internal motion, some weight had to be missing from the tally. The universe was cheating our senses by supplying extra gravity without supplying extra light. Then came the finer detail inside single galaxies. Measurements charted the motion of individual stars from the galactic core outward into the thinner disk. According to what we know of rotating systems, the farther from the center you go, the slower an orbit should be. Planets prove this around the Sun. Outer orbits move much more slowly than inner ones, a simple and elegant rule. But galaxies did not obey. The stars at the edge whipped around at almost the same speed as those nearer the heart. Laws of gravity should have tipped hundreds of billions of them over the edge. Yet galaxies stayed bound. That realization demanded something beyond familiar matter. Dust, gas, loose planets, all had been ruled out, either because they were visible in other wavelengths or because their collective mass was too small. It could not be faint stars either, or the effect would shine through in surveys. Whatever accounted for the grip acting on galaxies was not detectable in any direct way. This was not ordinary matter hiding in the shadows. It was a new category. Think of a skyscraper under construction. Visitors standing on the street see the glass exterior and luminous edges, but those bright details hide the real structure. The hidden frame of steel beams and trusses bears the weight. Galaxies seem to hide a similar frame, ghost scaffolding spread through space, invisible yet fundamental. Without it, the luminous parts would fall apart. With it, the entire edifice holds shape for billions of years. As instruments improved, more indirect signs appeared. One of the clearest was light itself, not shining from the hidden mass, but bending because of it. Gravity has the power to curve the path of light rays when they pass near massive objects. Astronomers tracking galaxies against far brighter backgrounds saw distortions shaped like smears and arcs. This was the fingerprint of strong gravity in action. It bent and magnified distant light into warped images. By comparing the visible matter against those distortions, a map of extra hidden mass could be sketched. Time and again, the mapped lensing revealed more gravity than visible stars could ever provide. Here was confirmation that the unseen was real, not a trick of flawed measurements. Clusters and galaxies showed arcs of distorted light pointing to the same conclusion, immense reservoirs of dark matter silently governing structure. It was as if gravity had betrayed the presence of a hidden architecture, one that refused to glow but influenced everything else in sight. More observations carried the same story. The pattern of cosmic background radiation, the afterglow of the early universe, showed subtle ripples that could only make sense if dark matter was already in place, tugging and shaping the distribution of hot plasma. The scale of matter in the modern universe matched the scale suggested by those faint ripples in the radiation left after the Big Bang. Across different epochs and tools, the verdict always circled back to the same unseen substance. The weight of this evidence grew until it forced a redefinition of the universe. Ordinary matter, the kind that burns in stars and forms planets, turned out to be an afterthought, a fraction of the whole. What needed to exist to explain the observed behavior was far greater in extent and mass. In fact, about a quarter of the entire universe's contents must be bound into this form of unseen matter. Compare that with the thin layer of baryonic matter we can actually see, and the scale of mismatch becomes staggering. Once you accept that conclusion, the universe we live in looks different. Every galaxy becomes not just a swirl of glowing gas and stars, but a small patch of light embedded in an immense, invisible halo. These halos extend far beyond the stellar disks, stretching wider and deeper than what eyes or cameras show. Without them, the universe of sight is incomplete, like a painting missing its canvas. The visible emerges, but the hidden medium bears its weight. The mystery sharpened. If this was not gas or dust or faint stars, then what was it? The answer lay beyond catalogs of ordinary matter. It was not known planetary debris or collapsed stellar remnants. Its mass was smooth, extended, and immune to radiation. It did not shine, it did not absorb, and it did not scatter the photons streaming past. Trying to detect it directly was like trying to hear footsteps in a sealed room. The effect would only register when it pressed on something large enough to shift under its weight. In essence, the universe itself revealed the presence of this new ingredient by refusing to behave without it. Massive structures stayed intact, light bent off course, and background radiation froze ripples too sharp to be explained otherwise. Each finding whispered the same message. There is an invisible presence woven into the cosmos, an unseen hand that steadies galaxies, clusters, and cosmic filaments. It is everywhere, silent yet indispensable. Astronomers worked the numbers, and the fractions spoke clearly. About 27% of the energy matter content of the universe is this unseen matter. Another chunk is ordinary atomic material, only a sliver. The rest is something even stranger, a repulsive energy accelerating expansion. But first came recognition that dark matter exists, that it carries the lion's share of mass, and that all visible stars are footnotes attached to its structure. We are left looking at an uncomfortable truth. Every beam of starlight is secondary to the hidden scaffolding binding it. Our galaxies owe their survival not to the glow that dazzles us, but to something we cannot see. And that raises the next problem. If this matter is not stars, planets, gas, or dust, and cannot be black holes in sufficient quantity, then what is it made of? The trail now leads not only to astronomy, but particle physics, where candidates for this strange matter have been proposed. And that is where the mystery deepens further, because if dark matter is not familiar matter at all, it must be something entirely new. You might think dark matter is just more hidden stuff. Rocks drifting between stars, vast clouds of dust, maybe legions of faint stars too dim to see. But it's not. Astronomers sorted through every familiar candidate, planets, compact stars, even black holes, and each failed the test. Ordinary matter, no matter how faint or cold, leaves footprints in the light we receive. If the cosmos were packed with it, we would have noticed by now. Take black holes. They sound like the perfect suspects, dense, invisible, and gravitationally powerful. But here's the problem. If billions of them filled galaxies, their presence would reveal itself constantly through lensing. Light from more distant stars would curve and split around them, creating flashes and brief echoes as the alignment changed. We do not see this happening often enough. Black holes do exist in great numbers, but not in the extreme populations needed to account for dark matter. Their distribution is too sparse. Their collective weight is too small. What about faint stars, brown dwarfs, or loose planets by the billions? These are called MACOs, massive compact halo objects. For a while it seemed plausible that hordes of such dim remnants were orbiting through the galactic halo unseen. But when astronomers tracked star brightness for sudden flickers caused by gravitational microlensing, the expected rate was absent. There were a few detections, but not nearly enough to add up to the cosmic shortfall of mass. If halos were packed with these faint objects, microlensing would occur far more frequently. It didn't. So MACOs failed to carry the load. Gas and dust were checked as well. Clouds can stay hidden in visible light, but they shine in radio and infrared wavelengths. Sensitive instruments designed to detect faint infrared emissions scanned deep into our galaxy. If dark matter consisted of normal atoms bound into gas, it would have glowed at these frequencies. Instead, observations proved the halos of galaxies are nearly transparent, so gas could not supply the weight either. Planets? Too small, too few, too reliant on formation from ordinary matter. Even imagining countless rogue planets adrift between the stars doesn't change the fact that there isn't enough raw baryonic material in the universe to make up for the missing 77%. Ordinary matter is capped. Cosmological measurements show you cannot hide that much extra atomic mass without disturbing signals from the early universe. The background radiation would carry the marks. It doesn't. The conclusion sharpened with each test. Dark matter is not built from familiar atoms. That forced researchers into a new frontier, unknown particles outside the standard model of physics. What if a population of invisible particles filled every cubic meter of space, barely interacting with atomic matter? These particles would not shine, not absorb, not scatter. They would slip through ordinary matter almost without trace, like ghosts in motion. The first candidates were called WIMPs, weakly interacting massive particles. Heavy, stable, and nearly collisionless, they could provide the extra gravitational pull while remaining unseen by telescopes. WIMPs became the leading theory for decades. Then came axions, ultralight particles theorized to solve another puzzle in particle physics, and sterile neutrinos, a more elusive cousin to the known neutrino. Each played by rules that made them frustratingly invisible. To imagine their nature, picture shadow particles, countless streams flowing through you right now. They pass through your body, the walls around you, and the planet beneath your feet without leaving a scratch. If they exist, billions would be moving through every square centimeter each second. Yet you never feel them because their chance of interacting with normal matter is almost zero. Only the cumulative weight of their presence betrays them, tugging on galaxies and bending the structure of space itself. Scientists built experiments to try to corner these particles. Deep below mountains and inside mines, detectors sit buried under thick rock to shield them from cosmic rays and radiation that would otherwise swamp the signals. In these depths, quiet chambers are filled with liquid xenon or cooled crystals held at temperatures near absolute zero. The idea is simple. If even one passing dark matter particle strikes an atom inside, that atom would recoil. The detectors are built to register such a faint disturbance, like listening for a whisper in the middle of a storm. Operating these experiments is an exercise in patience. Years can pass with no definitive signal. Occasionally a suspicious event will appear, but when checked and repeated, it fades into background noise. The detectors are remarkably sensitive, able to sense single photons or vibrations smaller than the width of an atom, yet the elusive particles continue to slip through their grasp. The global search continues across different designs: noble liquid targets, cryogenic sensors, scintillating crystals, all hunting for a trace. So far, not one candidate has survived the scrutiny of repeated tests. WIMP models were expected to show up in certain mass ranges, but decades of effort have ruled out large swaths of possibilities. Axion detectors, which use strong magnetic fields to convert these ghost particles into measurable photons, have yet to confirm a discovery. Sterile neutrinos remain a mathematical possibility more than an observational fact. Each new round of experiments refines the search, sharpening what cannot be with greater certainty. But the positive detection remains absent. There is a subtle irony here. Dark matter shows itself unmistakably in astronomy on the largest scales. Galaxies' orbit and light bends in ways that make its presence clear. Yet up close, in direct experiments, it slips away as if it does not exist. The universe announces it with grandeur, but the laboratory stays silent. Large numbers scream, small experiments whisper nothing. The contrast fuels both frustration and fascination. As years pass without a conclusive hit, the picture of dark matter grows stranger, not clearer. Perhaps the particles are even lighter than imagined, or heavier beyond the reach of current detectors. Perhaps theory itself is incomplete, and dark matter is not a particle at all but something different, something not yet framed in the language of physics. For now, the search presses on because the evidence in space is too strong to ignore. Underground laboratories continue to build larger tanks and more sensitive instruments. The hope is that Eventually, one of these rare ghost collisions will leave a signal that cannot be confused with noise, an event so distinctive it forces physics to accept dark matter into the known family of particles. Until then, the silence is deafening, but also instructive. Every null result shows us where the answer does not lie. The effort has lasted decades, involving hundreds of scientists across continents, yet the reward remains hidden. We know dark matter is not rocks, gas, faint stars, or black holes in massive numbers. We know it cannot be ordinary matter in disguise. By elimination, it must be something fundamentally new. That knowledge alone reshapes the way we look at the universe. The familiar stage props of stars and planets are not enough. The main act is hidden in particles we have yet to see. This long pursuit, testing failures more than successes, has left the scientific community balancing on a knife edge. The gravitational evidence is undeniable, but the microscopic proof remains missing. And as if one deep mystery were not enough, the story of the dark side of the cosmos grew even more dramatic at the close of the 20th century. For in studying expansion itself, scientists stumbled on a shock bigger still. The universe was not just bound by missing mass, it was being pushed apart by a new, unknown presence. Imagine expecting the universe to slow down under its own weight, only to discover that it is actually speeding up. For most of the 20th century, the assumption was steady. Gravity, being an attractive force, should act like a brake on cosmic expansion. The universe began in a flash of energy and space. It stretched, and over time, the pull of matter should gradually slow the outward rush. Maybe it would decelerate forever. Maybe it would one day collapse back. But in either case, the long view was a universe slowing under gravity's grip. That was the picture, and it seemed unshakable. Then, in the 1990s, came a different kind of test. Astronomers turned to exploding stars, type 1, a supernovae, to measure distances across vast scales. These stellar explosions occur when a white dwarf in a binary system reaches a critical threshold and runs away into nuclear fire. Because the mass at ignition is always the same, the brightness of these blasts can be treated like a rung on a cosmic ladder. Measure how bright they appear and compare it with the brightness they should have. That gives distance. Pair it with how fast their galaxies are moving away, and you can chart the scale of cosmic expansion across time. The expectation was clear. The more distant the supernova, the more ancient the light, and the stronger the deceleration should appear. Galaxies seen far away would have been slowing for billions of years under gravity's hand. But when the data came back, the results did not fit the expectation. Instead of showing a steady slowdown, the plots revealed something that seemed upside down. The galaxies were not just receding, they were receding faster with time. Expansion itself was accelerating. Picture it like this. Toss a ball upward. Gravity will slow its climb, stall it, and bring it down. That is the normal pattern. What the supernova data implied was the opposite. Toss the ball, and instead of slowing, it moves faster as it rises away from you. The force of gravity, which should be a brake, looked as though it had been overpowered by some hidden hand pushing outward. This was not a small detail. It flipped the story of the cosmos on its head. Instead of a universe bound to fade into a slower and slower sprawl or fold back on itself, it was racing ahead more rapidly as time passed. Expansion would not stop. It would not even slow. If this trend continued, galaxies would become more and more isolated, the gaps between them stretching wider on every scale. The long-term fate of the universe changed at a stroke, from an eventual slowdown or collapse to an endless race outward. The shock led back to a forgotten equation. Decades earlier, Albert Einstein had tried to balance his equations of general relativity by adding an extra term, the cosmological constant. He thought it was inelegant, maybe even a mistake, and later set it aside. But the supernova measurements brought it back. An energy inherent to space itself, constant and unchanging, could provide the repulsive force needed to explain the accelerating pace. It was as if empty space carried an inbuilt tension, a kind of pressure that worked not by pulling, but by pushing. At first it seemed strange to suggest that nothingness could have substance, but the mathematics of relativity allows it. If you treat the vacuum of space as more than an empty container, if you assign energy to it, the equations produce an expanding effect. Space not only hosts galaxies, but actively stretches them farther apart. This was a natural way to reconcile what telescopes were seeing with the laws of physics. Suddenly, Einstein's discarded term looked prescient rather than clumsy. Scientists gave this outward-pushing influence a name: dark energy. The label ranges far beyond an identity. It does not tell us what dark energy is, only what it does. It accelerates expansion, tipping the balance against gravity on larger scales. As far as we can tell, it appears uniform. It does not clump with matter or form structures. It works evenly, woven into the fabric of space itself, invisible but relentless. Even with that definition, the puzzle remains enormous. Is dark energy truly constant, unchanging through time? Or is it dynamic, a field that evolves or fluctuates? Does it tie back to quantum vacuum fluctuations, the jitter of energy predicted at the smallest scales? Or is it linked to something else entirely, perhaps even a breakdown in gravity's rules at the grandest spans of the universe? The questions multiply, but the evidence from the supernovae stands firm. Expansion is not fading, it grows stronger. If you were standing in the 1990s watching these discoveries unfold, the feeling would have been startling. Imagine expanding the deepest surveys, plotting positions and velocities meticulously, expecting a slowing graph. Then, as the points line up, realizing that trend is inverted. What the calculations asked you to believe is that a fundamental force works against every atom of matter. And it had been there all along, invisible to direct sight, until explosions of faraway stars acted as beacons. The consequences for cosmic fate are huge. In a universe ruled only by matter and gravity, there were essentially two paths. It could coast and fade slower and slower, or it could reverse. With dark energy present, the list of fates expands. If the repulsion is steady, the universe will grow colder and emptier, a so-called big freeze. If it grows stronger through time, the ending could be violent, the big rip, when galaxies, stars, and finally atoms are stretched apart. If it weakens or changes sign, it could still halt expansion someday. None of this was part of the old story. All of it depends now on the behavior of this invisible component that dominates space. So we step from one mystery into another. First came dark matter, the hidden anchor holding galaxies and clusters together. Now a new player enters, doing the opposite, not pulling, but pushing. Ordinary matter and energy make up only a sliver of reality, and yet we've focused on them for centuries because they are what we can see. The revised picture is stranger. The universe is governed by the unseen, and the brightest things in the sky are side effects rather than primary drivers. This recognition reshaped cosmology. Observations once recorded as oddities became critical data for constraining the properties of dark energy. Surveys multiplied using not only supernovae, but also maps of cosmic background radiation and the distribution of galaxies. Each provided an independent way to read the acceleration. Together they reinforced the conclusion. The universe rushes outward under a push we cannot yet explain. Einstein's idea of a cosmological constant rose from discarded scribble to center stage. Whether it is truly constant or a placeholder for deeper physics is an open question. What matters is the fact it represents, a pressure tied to space itself. Call it vacuum energy, or quintessence, or something else entirely, the effect in the 1990s was the same. Data showed expansion running faster. The cosmos carries a drive beyond gravity, and it cannot be ignored. In the end, this was the second great shock of modern astronomy. The first, dark matter, revealed invisible scaffolding holding structure together. The second, dark energy, revealed invisible tension ripping structure apart on the largest scales. Both must be reckoned with if we are to understand cosmic history and destiny. We discovered them because the universe refused to behave by the rules we assumed, and that leaves us with a sharper, deeper frontier. The stage is set for a new inquiry. If one mystery acts as an anchor and the other as a repelling force, then the play of the universe is not a simple push or pull, but a contest. We move now from the weight of hidden matter to the outward thrust of hidden energy. And the quest moves with it, from searching for unseen glue to confronting a cosmic anti-gravity that shapes the fate of everything. If 68% of the universe is powered by something we cannot describe, what might it actually be? That is the puzzle at the heart of dark energy. Gravity, we understand. Matter, whether luminous or hidden, can be weighed and mapped through its pull. But dark energy resists such straightforward handling. It behaves like an invisible pressure, showing up only in the accelerating expansion of space itself. And since it accounts for most of what exists, the stakes are enormous. The first way scientists tried to explain it was to return to the notion of vacuum energy. At first, this sounds counterintuitive. How can empty space contain energy? But in quantum theory, even a perfect vacuum is not truly empty. Fluctuations at microscopic scales create brief eruptions of energy that wink in and out of existence. If you add this up across the whole of space, the result is a measurable effect. Think of space as a stretched sheet. Even if nothing sits on it, the sheet can still carry tension. That constant tension would produce an outward push, uniform and unchanging, driving galaxies apart and quickening expansion. On paper, vacuum energy fits many observations. A fixed constant, always present, could explain why the push of dark energy appears smooth and evenly spread across the cosmos. It also ties neatly to the old cosmological constant term in Einstein's theory, yet here lies a striking contradiction. The predicted strength of vacuum energy from quantum physics is staggeringly larger than the amount inferred from astronomy. The mismatch spans many orders of magnitude. In other words, the math says the effect should be unimaginably intense, but the sky shows us a tiny, delicate pressure. One framework expects a flood, the other observes a trickle. Reconciling the two has proved nearly impossible. To escape that contradiction, another idea was proposed: quintessence. Instead of treating dark energy as a fixed property, quintessence imagines it as a dynamic field that changes with time and perhaps with location. Similar to how electric and magnetic fields permeate space, this field would carry energy that can evolve. Unlike the cosmological constant, quintessence could grow weaker or stronger over billions of years. It is a flexible answer, and that flexibility is its appeal. If future observations show dark energy's strength shifting even slightly, quintessence will gain weight as a candidate. The analogy that helps here is a spring. A spring stretched between two anchors holds potential energy. If it stays fixed, the tension is constant. That would be the cosmological constant version. But imagine the spring winding tighter or loosening slowly over vast stretches of time. The pull would evolve. That resembles quintessence, a changing field woven into the fabric of space. This model answers the fine-tuning problem by suggesting dark energy is not fixed after all, but reactive and variable. Still, quintessence runs into its own snags. The field would need to behave with remarkable precision to match what we see today. Too much variation, and galaxies would never have formed. Too little, and the difference from a simple constant becomes meaningless. To this day, no specific mechanism explains why such a field would settle exactly in the delicate range we observe. It solves one puzzle only by creating another. A third line of thought goes further, proposing that perhaps the mystery is not about energy at all, but about gravity itself. Maybe our current laws of gravity, so precise in the solar system and with stars, do not hold perfectly at cosmic scales. Modified gravity models suggest Einstein's theory of general relativity, while accurate locally, bends or breaks when stretched across billions of light years. If gravity weakens or changes form in that regime, acceleration could result without needing any exotic new energy. The metaphor here is infrastructure. Suppose you pave a road. For short trips, the surface seems smooth and solid, but stretch it across a continent, and cracks appear that only show at full scale. Gravity might be similar. The equations work beautifully when applied to orbits and local motions, but strain under the demands of cosmic span. If they need adjustment, the acceleration we attribute to dark energy could instead be a symptom of gravity's limits. The challenge is that each of these approaches, vacuum energy, quintessence, and modified gravity, can be tuned to reproduce the acceleration curves we observe. On graphs of expansion rate over time, they can all be made to look plausible. Practically, they act unseen and subtle, layering effects into the cosmic web that only reveal themselves indirectly. They do not produce sharp signatures that can be easily separated. Observational data struggles to distinguish between them. Supernova brightness, large-scale galaxy surveys, and cosmic background ripples each support the need for a repulsive effect, but they do not in themselves tell us whether that effect is constant, changing, or a revision of gravity. It is like hearing an echo in a cave. The sound undeniably arrives, but whether it came from one wall, many walls, or a hidden chamber is much less clear. This situation builds a peculiar tension in science. We know the effect must exist. We can chart its consequence on galaxies, clusters, and even on the shape of the universe itself. But every theoretical frame that tries to give it identity meets a wall of contradictions. Vacuum energy predicts the wrong magnitude. Quintessence looks too finely balanced. Modified gravity undermines equations that succeed in other arenas. None are decisively tested or falsified in the lab. Even powerful experiments have yet to draw sharp lines. Measurements of cosmic microwave background anisotropies or maps of how galaxies cluster in space fall into ranges that all leading models can satisfy. No design yet can pin the answer down. It leaves us with educated guesswork, sharpened against one stubborn fact: galaxies drift apart faster as time proceeds. Every new telescope simply affirms that this drift is real. Why it happens is still open. From the standpoint of physics, this keeps dark energy as the most potent but least defined player in the universe. It carries more share of cosmic content than dark matter or ordinary matter combined, yet it sits nameless. We describe what it does, not what it is. For now, its role is like a blank character in a play, dominant, central, but undefined by dialogue. And that is what makes this problem so unnerving. We live in a universe where the majority share is known only by effect. We can map dark matter structures as invisible scaffolds. We can weigh their grip through lensing and orbital speeds. But dark energy goes further. It stretches the fabric of space itself, accelerating everything outward, and still resists a precise description. The models remain competing sketches, none crowned as truth. So when we say dark energy accounts for most of the cosmos, it is less a resolved statement and more a placeholder. It acknowledges the gap rather than filling it. Each hypothesis points in a different direction: constant vacuum tension, evolving field, or change to fundamental gravity. But none yet settles the case. Until sharper tools arrive, our picture of the universe remains incomplete. We know the engine is running. We feel the acceleration in every measurement of distant galaxies. But what type of fuel powers it? Nobody can yet say. That is why dark energy continues to occupy the central, unanswered seat in modern physics. And while these ideas remain suspended, another balance shapes reality itself. One hidden force pulls galaxies inward, giving them structure. Another hidden force drives them outward, pulling space apart. Together they set the stage, and to judge their contest is to understand the fate of everything. The universe is a battlefield between two invisible giants. On one side, dark matter pulling with steady grip, binding galaxies into shapes and holding clusters together like unseen anchors. On the other, dark energy stretching fabric itself, driving expansion forward with an accelerating push. Neither can be seen. Both show their hand only in what they do to everything else. Between them lies the balance that shapes the past, present, and future of the cosmos. Dark matter acts as the glue. Without it, galaxies would scatter like sparks from a fire. Its gravitational pull provides the framework, an invisible scaffold girding halos far wider than the disks of stars. It bends light into arcs. It speeds and steadies rotation. It lets filaments of matter form from seeds of early expansion. If all you counted was visible atoms, nothing of today's large structures would stand. If you add this hidden tool of gravity, cosmic architecture suddenly makes sense. Now, place dark energy on the stage. Here is no anchor, no glue. Its role appears opposite. Instead of binding, it repels. Dark energy distributes evenly, woven into every patch of space. It does not gather into clumps or halos. Rather, it pushes from within, stretching distance itself. The farther apart galaxies drift, the more room there is for dark energy to act, and the stronger its influence grows. What seems silent at small scale becomes overwhelming when stretched across billions of light years. The contrast is sharp. Dark matter builds. Dark energy dismantles. One knits clusters and webs together. The other chips those connections apart by pulling the threads of space wider with time. Side by side, they form a natural tension. The glue versus the spring, the inward claw and the outward stretch. Neither feels dramatic when you stand on a single planet. But across the story of the universe, their contest decides whether galaxies form, whether stars have fuel, and whether space accretes or empties. You can picture this tug by holding a sheet of rubber. Press a marble into the center, and the shape curves in. More marbles, more dimples, bending and drawing inward. That is what dark matter does, creases in the sheet-gathering structure. Then, take your hands and pull that sheet outward. The whole surface stretches, dimples flatten, edges separate, structure weakens. That is dark energy, tension, pulling the fabric itself. The sheet metaphor is simple, but it shows how opposing forces play across the same field. Look at clusters of galaxies as evidence. Their bonds reveal dark matter's hand. Dozens of galaxies orbit in shared halos, speeds too high to remain bound without an extra, non-luminous weight. Inside clusters, dark matter holds sway, giving cohesion. Step out farther to hundreds of millions of light years, and you see acceleration taking over. Measurements of redshift show galaxies moving apart faster than gravity alone could spare. The larger the scale, the stronger the outward push becomes. So which side dominates? At the scale of a galaxy, dark matter clearly wins. It binds stars into disks, centers into spirals, halos into coherent forms. At the scale of the known universe, dark energy takes the crown. Its uniform push grows as distance extends. For billions of years, dark matter resisted, buying time for stars and planets to arise. But data show that now, on the grandest scales, the repelling energy has overtaken gravity's hold. Expansion quickens with age. Right now we live during a rare stage when both forces matter at once. In earlier epochs, matter density was higher, making gravity the lead actor. Expansion slowed, structure condensed, galaxies formed. Later epochs will run under dark energy's reign, expansion outpacing any pull, galaxies racing from view. Our era lies in between, a crossing point where both shapes influence strongly. We can watch galaxies still suspended in dark matter halos, while simultaneously measuring space accelerate outward due to dark energy's pressure. It is easy to forget how fragile this timing is. If dark energy had been stronger early on, structure would never have formed. Stars, planets, chemistry, none would have had time to assemble. If weaker, the universe would still be slowing, perhaps even turning inward. That we exist in this balance means we live within narrow conditions, a cosmic middle ground. Both hidden players act intensely now, letting us study their dual impression. At smaller scales, such as a star system, dark matter and dark energy remain hidden. You would not measure them in classroom experiments or even solar orbits. Gravity of ordinary matter dominates locally, but step onto galaxy scales and you see the extra pull of matter that does not shine. Step farther still between superclusters and you see the extra push of energy tied to vacuum itself. This scale dependence makes the tension nuanced, not flat. Even so, the impact is absolute. Every star that forms, every planet that cools, every galaxy that drifts falls under this cosmic tug. You can think of it as two hands on a rope, one pulling tight, one pulling wide. There is no neutral ground, only struggle. The question of which one leads shapes every projection we have of cosmic destiny. At present, data show dark energy winning. Acceleration overwhelming gravity once distances break into billions of light years. But local space remains stitched by dark matter, defending stars and clusters for long epochs to come. This delicate duel shows itself in the maps of the cosmic web. Filaments of matter lace the universe, beads of clusters linked by bridges of invisible glue. But when those bridges stretch, gaps widen. Void regions become larger, emptier, stranger. Over time, the chart of filaments will thin as dark energy pulls the sheet outward. The scaffolding will remain locally, but the grand network will thin. Cosmic solitude will spread. In practical terms, the long-term fate of the universe hinges on this tension. If dark energy is fixed in strength, expansion will continue forever, galaxies vanishing beyond reach one by one, leaving the big freeze. If it grows stronger, the big rip waits, tearing clusters, stars, and atoms. If it shifts differently, another outcome might arise. But in all cases, the roles of matter and energy together decide. This is why both subjects demand equal attention. To grasp the framework of matter without the push of energy leaves the picture broken. To measure the acceleration without the scaffold misses half the story. Both forces shape an ongoing play, one knitting, one unraveling. And right now, in our present era, both still run strong enough to be measured. That is a rare window, one that will not last on cosmic timescales. The lesson is stark. The future of every star, planet, and galaxy depends on how this tug of war unfolds. The fate of clusters, the scope of sight, even the span of chemistry and life as we know it, all ride between invisible giants. Their struggle defines the possible endings. It defines what kind of universe opens tomorrow. And because of that, the pursuit to pin down their properties becomes more than curiosity. It becomes essential. To measure the strength of dark matter and the nature of dark energy is to understand where all of this is headed. That is why today around the world, laboratories and telescopes work in tandem. The hunt is on, driven not only by mystery, but by the knowledge that hidden giants already steer our destiny. The search for dark matter often begins in the most unlikely places, deep underground, far from sunlight and cosmic storms. At first it sounds counterintuitive. We are looking for something that seems to fill the universe, yet we choose to chase it in caves and shafts. But the reason is simple. To hear the faintest signal, all background noise must be silenced. Cosmic rays slice through the atmosphere every moment, striking detectors with a constant drizzle of energy. The sun bombards us with particles as steady as light itself. On the surface, even the most sensitive chamber would be deafened within seconds. So experiments retreat underground, carving out private darkness where rock acts as a shield. Mountains and mines block showers of interference, creating quiet pockets that offer the cleanest listening posts we can build. It is there that detectors, some the size of swimming pools, sit in stillness, waiting for a ghost particle to touch them. Inside these laboratories, extraordinary instruments stand guard. Picture a tank filled with many tons of liquid xenon. Xenon is chosen for its exceptional purity and its ability to flash faintly in response to a collision. When cooled to liquid states, it becomes both target and witness. If a dark matter particle were ever to strike a xenon nucleus, the atom would recoil and release a tiny flash of light along with a few free electrons. Sensitive photomultiplier tubes, or silicon sensors, ring the chamber, tuned to catch that glimmer. Each pulse could be the long-awaited whisper of dark matter reaching us. Other designs use crystals cooled to near absolute zero. In those detectors, an atomic recoil would make the crystal lattice vibrate ever so slightly. At such cold temperatures, tiny vibrations become measurable as electrical signals. Another design stacks layers of scintillating material that spark when disturbed. All of these approaches share one principle. They serve as traps, fine enough to catch one improbable touch. Each recoiling atom is like a drumbeat in silence. One beat would prove the existence of a hidden realm of matter. But these potential signals are buried under countless imitations. Natural radioactivity in the surrounding rock, or even the decay of atoms inside the detectors themselves, can mimic the signal. That is why layers upon layers of shielding surround each detector, lead, copper, and water tanks, stacked like nested shells. Scientists work tirelessly to eliminate every trace of mundane noise so that what remains is only the rarest events. The paradox is that as instruments grow more sensitive, they also become vulnerable to smaller and smaller imposters. It is as though by building the sharpest ear, you also invite every tiny creak and sigh to masquerade as something profound. Waiting for a genuine strike takes patience. Years may pass without a single candidate. Even when candidate events appear, they must be tested and retested. Often they fade into the statistical haze, leaving no solid claim to discovery. In that sense, the hunt becomes like waiting for a single whisper in a storm, straining to hear a signal that may come once in a decade, or perhaps never at all. You might imagine these experiments as solitary, hidden projects. In truth, they operate in parallel across the globe. Multiple sites build different designs in different caves, each one acting as a cross-check to the others. If a genuine dark matter event occurs in one chamber, the hope is to see the same pattern reflected elsewhere. This global coordination makes the search both more credible and more ambitious. If evidence arrives, it must survive scrutiny against dozens of detectors running continent to continent. Only then would the discovery secure itself as fact. So far, not a single event has stood firm under that scrutiny. Flashes have come and gone, debated for years, but every supposed discovery has dissolved into background or experimental error. From one view, that absence is frustrating. The signal we expect has failed to show. From another, it is clarifying. Each non-result closes one door and forces theory to adapt. It rules out specific masses or interaction strengths for dark matter candidates. With every failed run, the unknown range narrows. The technology itself is a marvel. Imagine lowering a chamber of liquid xenon large enough to fill a truck into an underground cavern, then cooling it with precision systems so that the noble gas stays liquid. Photomultiplier tubes sit in darkness for months, logging bit after bit with silent patience. Or picture a crystal cooled to a fraction above absolute zero, so cold that vibrations from an atom's recoil would stand out. These are feats of engineering built against the odds. They remind us of what science can do when chasing something too quiet to hear in everyday life. And although results have not yet delivered the definitive catch, these detectors remain our most direct line to unseen matter. Think of them as nets cast into still waters. They show us nothing on the surface, but we keep them submerged in hope. Because if the net ever twitches, if a genuine particle collides and produces a true signal, that moment will change physics as deeply as any discovery of the last century. To prepare for that possibility, the next generation of detectors grows even larger. What once used a few hundred kilograms of material now scales to tens of tons. Shielding grows thicker. Sensors become sharper. Each new version deepens the silence so that even rarer interactions might stand out. This scaling mirrors the patience of the hunt itself: bigger chambers, longer timelines, finer resolution. It reflects a simple belief that persistence will outlast the secrecy of the universe. As we wait, the story takes on a human tone. Imagine being part of these experiments, arriving each day to a cavern where lights are dim, machinery hums quietly, and noble gas sits in still, cold tanks. Days blur into years. Datasets pile up to immense size. Most of it shows emptiness. Yet always there is the possibility, however slim, that the day's data may hold a new clue. The dedication here is as immense as the subject, life devoted to patience in search of a single strike. And this is the irony. We know dark matter must exist on cosmic scales because its gravitational pull is clear in galaxies and clusters. Yet in direct searches, nothing has been caught. These underground halls are the crossing point of contradiction. The universe shouts its message across billions of light years, but when we listen closely, the voice is silent. Still, scientists do not step away from the cave walls. They refine, they expand, and they wait. Because if dark matter is ever captured, it will likely be in silence, beneath rock, far from the noise of cosmic rays. There, hidden tanks continue to watch with patience, the closest link we have to a hidden substance that outweighs the stars. And while these depths hold our ears to the ground, the search follows another path as well, one that does not hide underground, but smashes matter together at the highest energies on Earth. The frontier of accelerators waits at CERN, where collisions may birth the very particles these caverns seek. Could smashing matter apart at nearly the speed of light reveal ghostly particles floating in the cosmos? That is the goal of the largest machine humans have ever built. A ring buried beneath the ground, stretching for kilometers, is designed to take ordinary particles, accelerate them into tight beams, and collide them head-on at breathtaking energies. Each collision lasts only a fraction of a second, but recreates physical conditions similar to those after the Big Bang. In those brief instants, the hope is that something beyond familiar matter may show itself, an unseen particle that explains the gravitational pull we call dark matter. The collider was conceived with a simple guiding principle. If you cannot catch dark matter drifting through detectors, perhaps you can create it. The early universe produced every known particle through extreme heat and pressure. By reproducing those conditions, the same recipe might form the hidden ones too. The advantage of this method is control. Instead of waiting years underground for a single rare interaction, particle physicists smash beams together trillions of times, recording each outcome. Every unequal energy balance, every missing fragment is logged. In that mountain of information, they search for patterns that could mark new particles. In practice, a collision creates a spray of fragments. Protons, which make up the beams, are not solid marbles, but bags of quarks bound by gluons. When they collide, these contents explode outward. Hundreds of particles scatter like debris from a demolition blast. Tracking them requires detectors the size of buildings, layered with sensors. Each ring of sensors acts like a forensic tool. One measures momentum, another energy, another catches particle tracks. Move outward far enough, and each layer reconstructs the event in remarkable detail. Like peeling layers of an onion, the detectors strip down what happened step by step. The challenge is knowing what to look for. Familiar particles create signatures we already understand. Electrons curve one way in magnetic fields, muons punch deeper, photons trigger flashes, and so on. But if in all that chaos something fails to appear, that absence is a clue. Conservation of energy and momentum is strict. Nothing vanishes without a trace. If the tally at the end of a collision falls short, it suggests some invisible particle carried energy away without interacting. Missing energy becomes the breadcrumb, a silent track pointing to what detectors cannot see directly. This approach echoes how neutrinos were first identified. Decades ago, scientists noticed beta decay events where energy did not balance. They concluded another particle must be fleeing the scene unseen. That prediction, tested later, proved right. Neutrinos stream through us in their trillions each second, confirmed by detectors but first inferred by missing energy. The hunt for dark matter at the collider is built on the same reasoning. The difference is scale. Neutrinos are light and weak. Dark matter is thought to be massive and elusive. But the logic holds. Find the missing energy, and you may uncover the identity of a ghost particle. As experiments began, expectations surged. Within the first years of high-energy runs, detectors revealed new insights into particle physics. The most famous was the confirmation of the Higgs boson, the particle tied to the mechanism that gives mass. That was a triumph decades in waiting. Yet, beside the signature of Higgs, the anticipated fingerprints of dark matter did not show. No unexplained missing energy signals survived thorough checking. Particles appeared, behaved as expected, and the great reservoir of dark matter stayed hidden. This absence stirred debate. Perhaps the candidate particles, like WIMPs, exist at higher energies than the machine had yet reached. Maybe their interactions are even weaker than imagined, slipping through without trace. Or maybe the whole assumption that dark matter is a particle discoverable in collisions is flawed. Each possibility remains open, and the collider continues to push into uncharted ranges. Upgrades raise beam energy, sharpen detectors, and extend the scope of what might be produced. Though the search remains unfinished, the principle is clear. The collider creates extreme conditions where hypotheses about hidden matter can be tested. If dark matter particles exist within the accessible energy range, collisions remain the best chance to detect them through missing energy alone. In effect, smashing matter apart gives us a laboratory echo of the first second of the universe, where hidden components might show themselves once again. That is the payoff. The collider produces conditions unattainable elsewhere, a direct recreation of the forces that shaped matter itself. The scale of detection is staggering. ATLAS and CMS, two of the main detector sites, are more like cathedrals of science than simple instruments. Layers of steel, silicon, and magnets chart the path of microfragments with precision measured in fractions of a millimeter. Computers analyze streams of data so immense that only a handful of recorded events survive filtering for later study. Each chosen event might contain the fragment of a clue, a possible deviation from the standard model, a path leading into dark territory. The patience demanded here mirrors the underground hunts, years of watchfulness for traces that may never come. Yet progress lies in persistence. Every round of data rules out another possibility, tightening the map of what dark matter can and cannot be. If it is not seen in the mass range probed, theories adjust. If no missing energy signals survive, physicists sharpen their models once again. For science, negative results are not failure. They are narrowing steps. They prune the possible and steer effort where it is most needed. Each run of the collider carves away simple answers, training focus toward what remains. In the background, engineering pushes forward. Magnets grow stronger, detectors gain finer resolution, and digital analysis quickens. Every upgrade extends the collider's reach. As beams run with higher luminosity and broader energy windows, the chance increases that hidden particles, if real, will finally show their presence. Whether as subtle missing energy, or as unexpected decay channels, or as deviations in known patterns, the signal would stand out cleanly only after extraordinary precision clears the noise. What matters is that the collider provides a parallel path. Underground experiments listen for passing particles. The collider tries to manufacture them in controlled bursts. Both tackle the same riddle from opposite directions, and each strengthens the other. If a candidate particle hints itself in a detector underground, the collider could produce its cousin to confirm it. If the collider shows unexplained missing energy patterns, underground labs could check for the same particle streaming through Earth. The strategies converge into a coherent pursuit. No confirmed dark matter particle has yet emerged from the noise, but the attempt itself deepens our understanding of matter and energy. The absence of discovery is knowledge, proof that the answer lies on scales or rules beyond those we first guessed. The collider, by reproducing tiny slices of the early universe, acts as a gate. It is not only a machine for smashing, but one for sculpting questions more sharply. Through its crashes at near light speed, it refines what dark matter could truly mean. For now, the particle chase continues. Each burst, each collision, each data run hammers a little harder on the door of the unknown. Where galaxies whisper about hidden weight, the collider tries to shout it into existence. It is a bold parallel approach to the quiet tanks buried underground. And yet, no matter how high an accelerator reaches, it cannot probe the mystery of cosmic expansion itself. For that, different tools are used, not colliders but observatories that measure whole swathes of space. To test dark energy, we must turn from the underground and the accelerator tunnel to study forces shaping billions of light years. You need observatories not on the ground, but in space. Only beyond the atmosphere can instruments see faint galaxies without distortion. Only above Earth can you track the delicate clues written in ancient light. For questions as large as dark matter and dark energy, telescopes orbiting in silence are our best chance to witness what unfolds on scales impossible for laboratories or minds to recreate. Unlike particle accelerators or underground detectors, these observatories are not chasing single particles. They study patterns stretched across the cosmos, shifts in light from galaxies, arcs bent by gravity, and faint ripples frozen since the first seconds of the universe. In space, detectors act not as microscopes, but as panoramic cameras, each capture spanning millions of galaxies. They do not look for the particle itself, but for the signature of how it reshapes the universe. Among these instruments is the James Webb Space Telescope. Its mirrors and infrared sensors are tuned to peer far into the past, seeing light that has taken over 13 billion years to reach us. That light comes from galaxies forming during the early chapters of cosmic time. By charting their shapes, sizes, and clustering, Webb provides data about how galaxies assembled under the pull of dark matter. Its measurements give us the scaffolding points, the anchor marks, that models use to test how much unseen mass pulled threads together. Where Webb gives depth into the early universe, Euclid spreads wide. Its mission is to map billions of galaxies, not a few at record distances, but an immense sweep across cosmic volume. Euclid uses wide-field imaging and spectroscopy to measure both the shapes of galaxies and the redshifts that show how fast they move away. These two datasets work together. Shapes distorted by gravitational lensing show where dark matter lies, while redshifts track how expansion itself changes over time. Through billions of galaxies, a pattern forms, a chart of structure growth over cosmic eras. The Vera C. Rubin Observatory, though rooted on Earth, shares this mission through a wide-field survey unlike anything ever attempted. Night after night, it will scan the sky, capturing entire swathes in repeated exposures. Over years, its data will show how galaxies shift, how lensing signals stretch, and how clusters evolve. Its cadence turns snapshots into a movie, letting astronomers follow the story of matter distribution. Subtle shifts in brightness and position reveal gravitational fingerprints that otherwise remain hidden. Together, these three projects can weave a map of both dark matter and dark energy. Lens distortions show where matter hides in filaments and halos. Redshift surveys reveal acceleration, showing how expansion changed through billions of years. Early galaxies record how seeds formed in dark matter wells. Put together, the data might finally say whether dark energy is fixed or evolving, whether its strength grows, fades, or stays constant. If dark energy is steady, the universe freezes. If it changes, other endings await. These telescopes hold the key. Gravitational lensing stands at the center of this work. When light from far galaxies passes near mass, the path bends. The heavier the invisible matter, the sharper the distortion. By measuring millions of these distortions, space telescopes draw shadow maps of hidden mass, revealing filaments stretching between clusters like strands of an invisible web. Where halos grip galaxies, signal appears. Where voids spread wide, light passes almost untouched. It is like mapping wind by watching how tree branches sway, an indirect but precise method. At the same time, redshift surveys offer another line. Light stretches as space itself expands. Galaxies farther away appear redder, and the amount of redshift shows how fast expansion has carried them. By measuring galaxies at different distances, astronomers build a graph of expansion over time. This graph shows whether the universe slowed early on and when acceleration took over. Dark energy's fingerprint lies in this curve. It is where we see space overtaking gravity. James Webb deepens this record. By probing faint and early galaxies, it fixes endpoints for the models. Its infrared reach shows how galaxies formed when matter was dense and dark energy's role was minimal. Comparing then and now traces the handoff from gravity to repulsion. Euclid, with its enormous survey, provides raw numbers, galaxies in the billions, arcs in the millions, statistics strong enough to test models. Rubin adds time, following changes frame by frame, catching new lenses, and measuring how distortions evolve. Each telescope provides one angle, and only in combination do they reveal the full story. Think of it as triangulation in engineering. One tool measures depth, another breadth, another time. Only by combining them can you fix position. Cosmic mysteries demand the same approach. Telescopes across orbits and hemispheres provide complementary data, like surveyors mapping terrain too vast for a single eye. The payoff is potentially decisive. With these eyes in orbit and on mountain peaks, science may soon say with clarity whether dark energy is just a constant, a vacuum tension stretching space at every moment, or something dynamic that shifts with epoch. If maps show subtle change, then theories of evolving fields gain weight. If data remains steady across all eras, measured, then vacuum energy remains the simplest answer. Either conclusion narrows the unknown sharply. For dark matter, too, the benefit is immense. Particle labs wait in silence, but telescopes already see its gravity sculpting galaxies. By comparing models of particle behavior with the mass maps drawn from lensing, scientists can test which invisible candidates match the observed scaffolding. If dark matter is cold, structure aligns one way. If warm, another. Observatories refine these choices, narrowing what dark matter can be. None of this is instant. Missions like Euclid will take years to collect, calibrate, and release data. Webb operates at the edge of precision, its mirrors cooled to cryogenic stillness to catch faintest light. Rubin Observatory, with millions of nightly images, will amass petabytes of raw material. Processing, cleaning, and analyzing such torrents requires dedicated effort. But this slow accumulation is the only way to shrink one of science's broadest uncertainties. In a sense, these observatories turn the sky itself into a laboratory. Instead of waiting for single events or smashing protons, they use the universe as the experiment. Every galaxy is a data point, every arc of lensing an equation, every spread of redshift a marker of time. The universe writes its secrets across the sky, and telescopes in orbit let us read them without the blur of atmosphere or the glow of ground light. The global nature of the hunt becomes clear here. Underground detectors in mines, accelerators under fields in Europe, observatories on mountaintops, telescopes floating in space, all move toward the same aim. Each method addresses a different piece. None is sufficient alone. Together they make a planetary scale laboratory, instruments spread from rock chambers to orbiting mirrors. It is a coordination without borders, all aimed at a shared ignorance. And the stakes could not be higher. If dark matter is captured, physics gains a new set of particles. If dark energy is pinned, cosmology learns the true fate of time itself. The universe does not reveal its end easily, but with eyes in orbit, charting billions of galaxies, we at least have a chance to read the signals written across deep space. That is why this era is unique. Never before has humanity operated instruments this far into infrared, this wide in survey reach, this rich in repeated imaging. We are mapping the invisible at scales as vast as the questions themselves. And as these maps take shape, the outcome flows into one unavoidable truth. The destiny of the universe depends on what they find. If dark energy rules the cosmos, how does it all end? That's the question that moves from astronomy into philosophy. Every observation of expansion forces us to confront not only what the universe is made of, but where it is going. Across decades, scientists have narrowed the options into a handful of scenarios, each depending on how this mysterious outward push behaves across time. The first path is the simplest. If dark energy remains constant, if its effect stays as steady as measurements imply, the universe heads toward what is often called the Big Freeze. Expansion would continue forever. Over billions, then trillions of years, galaxies would drift farther apart. Light from one system would no longer reach another. Stars would die. Galaxies would wither into dust. Black holes would evaporate by slow radiation. The universe would grow darker and colder until nothing remained but thin radiation dispersed across immeasurable gulfs. It is not dramatic in a single moment. It is an ending by attrition, silence spread across infinite time. But what if dark energy does not remain steady? What if its strength grows with the expansion it controls? In that case, the universe becomes unstable. At first, galaxies would separate, then clusters, then stars within galaxies. Later, solar systems would be torn apart. If the acceleration continues to grow without bound, even the atoms themselves would lose their bonds. This scenario is called the Big Rip. It paints the cosmos as a fabric stretched until every thread snaps. Where the Big Freeze imagines endless cold, the Big Rip spells an abrupt and violent dissolution. There remains a third possibility, one that inverts the story completely. Suppose dark energy is not constant. Suppose it can change sign, shifting from push to pull. In that case, expansion would slow, stop, and then reverse. Gravity would regain dominance. Galaxies would drift back. Clusters would draw inward. Temperatures would skyrocket. In the final stages, the entire cosmos would collapse into a singularity. The universe that began in a hot expansion would end in a hot contraction. This outcome is called the Big Crunch. It would mark the universe not as endless, but cyclical, capable of repeating expansions and contractions across ages. The range of endings, each wildly different, arises from the same unknown. Dark energy controls the pace of expansion, but its nature remains hidden. Whether it is constant, dynamic, or a misreading of gravity, its future determines the universe's fate. To make sense of this, imagine a pendulum. Place weights along its arms, and its motion shifts dramatically. A slight move of weight one way slows it, a shift the other way speeds it. The exact balance determines whether the system swings steadily, erratically, or collapses back on itself. The cosmic pendulum works with invisible weights. Dark matter, dark energy, and gravity interact with ratios that tip destiny in one direction or another. What makes this contest more precarious is how delicate the balances are. If dark energy is even slightly stronger than constant, an eventual rip looms. If slightly weaker, a big freeze follows. If it reverses, then collapse waits. A hair's difference on cosmic scales sets the trajectory for everything. From our vantage point, no experiment yet pins the value perfectly. We measured trends with surveys of galaxies, with redshift maps, with cosmic background imprints. But the certainty we crave remains out of reach. The conflict runs deeper because each ending contradicts the others completely. A big freeze relies on endless time with no sharp transition. A big rip collapses existence into fragmentation long before eternal night arrives. A big crunch reverses direction entirely, dragging every atom back toward one point. No middle ground reconciles them. Until dark energy's identity is solved, all stand as possible. Right now, evidence tips toward one outcome: data from supernovae, from lensing surveys, from cosmic background fluctuations favor a steady form of dark energy. That result aligns with vacuum energy, the idea of a fixed cosmological constant. If this holds, then the big freeze is the most likely scenario. The universe expands forever, isolating galaxies until none are visible from one another. Stars run out of fuel, black holes fade, matter becomes thin gas, and eventually even the gas disappears. Endless time remains, but time is stripped of events. It means we live in a remarkably narrow window. In the grand scheme, stars only shine for a fraction of the universe's life. Our moment falls inside that span. We exist while galaxies burn bright, while structure still holds networks, while light still crosses from star to star. Billions of years from now, that will not be the case. Whatever life exists then will find a silent sky, absent the crowded brilliance we take for granted. This gives humanity's presence a curious importance, not because we control cosmic destiny, but because we simply exist during its visible era. We are here to chart galaxies across a vivid sky, to measure the structures bound by dark matter and torn by dark energy. In a sense, we occupy the middle act of the universe, the interlude where stars blaze and observers can ask questions. The final acts, whether freeze, rip, or crunch, will not allow such witnesses. To think of destiny this way is to accept how dependent we are on hidden components. The drama of endings is not guided by ordinary matter at all. The atoms we know, stars, planets, even life itself, play no role in deciding how the universe ends. The choice belongs to unseen players. Dark matter shapes structure in the beginning, and dark energy points the arrow to the end. It sharpens why the search for answers matters. The story of dark matter and dark energy is not background curiosity. It determines the fate of everything. If we want to know where all of this leads, where galaxies go, where time itself bends, we need to know which of the three fates the universe is walking towards. At this moment, the leading line points to an endless, frozen acceleration. But with uncertainty intact, the pendulum could still swing. We live then in suspense. Not the suspense of tomorrow, but of eternity. The experiments we build, the telescopes we launch, the theories we refine, all sift the question of which ending will unfold. The answer is locked into the hidden nature of dark energy, and until we crack it, the final chapter of the universe remains unwritten. Which leaves us at one last step, the question of why any of this matters for us, now. If 95% of the universe is hidden, yet it shapes both our beginnings and our end, understanding it may be the most important pursuit we can make. And that thought leads us to the closing frame, the mystery itself, and why we keep reaching into the dark to solve it. 95% of the cosmos is invisible, yet it shapes how galaxies form, how space stretches, and how the universe may end. What we call ordinary matter, stars, planets, and ourselves, exists on the margin, not the core. If we can decode dark matter and dark energy, physics itself will change as sharply as when relativity rewrote Newton's framework. That scale of revision waits in the shadows, hidden but decisive. The universe hides its secrets in the dark. Slowly, through machines underground, collisions at light speed, and telescopes above the atmosphere, we are learning how to see.